It is a great pleasure to have here in giving a Colloquio De Giorgi at Scuola Normale, Professor Christopher Deninger from the University of Münster. Let me just say a few words. Deninger is a distinguished mathematician in several fields. I had the fortune of meeting him long ago in the early 90s. And although our fields were somewhat different, I had the fortune to learn quite a lot of things very far from my mathematical panorama. He has many mathematical views, especially connecting different fields, the interplay between geometry, topology, arithmetic, and more. Among his work, I would like to quote, for instance, near to my field, his work on the special values of L functions. And the L functions are of the utmost importance from many viewpoints, in analytic number theory, for instance, but their special values at certain particular points carry information of geometric and algebraic type, which is very imaginative to detect. And Deninger did this. Among these values, we may remember the first results historically were the Leibniz expression for pi over 4 and Euler's expression for the sum of the reciprocal squares as pi square over 6. So this has a long history. But Deninger's work is by no means limited to this. He worked in many other directions, including arithmetic geometry, foliations, and so on. He has several honors. Let me mention just fellow of American Mathematical Society, and has been a plenary speaker at International Congress of 1998. So today the title is also very attractive. He will speak, tell us about primes, knots, and periodic orbits.
Yeah, thank you very much for the introduction and the nice words, and also for the invitation to Pisa, and especially for the invitation to this colloquium. I don't know what the rule is. Can the speakers take off the mask? Is that okay with you? Okay, then maybe because that's a little bit easier. So, as Umberto said, the title is Primes in the sense of prime numbers, knots, and periodic orbits. And this developed, or my approach developed out of the wish to understand the things about the Beilinson conjectures, these special values conjecture, which I had done previously, because in those conjectures you showed, the Beilinson conjectures tell you that a special value of some L series, for example, of an elliptic curve, should be something coming from K theory, etc. And if you plug in everything you know about elliptic curves, then you can show that both sides are the same. And the same conjecture for modular curves, you have to plug in everything you know about modular curves, and you can show something. But why it should be true in general, no one knows. And so all this is a journey to understand this. So let us start with the oldest analogy, knots and primes. What do prime numbers have to do with knots? And first I have to tell you how to geometrize a prime number. So I have to tell you what is a scheme. So the scheme is an object of modern algebraic geometry introduced by Grodendic. And affine scheme will start with a commutative ring R, and you attach to it spectrum of R. And this functor is contravariant, so it changes the direction of the arrows. And this is a geometric object. So as a set, this is the set of prime ideals in R. Not only the maximal ideals, like for example in the theory of C-star algebras, prime ideals, and plus the topology, so-called Zariski topology, which is very weak. It's not even Hausdorff, plus a notion of what are the good functions on this. So that's a structure sheaf where you tells you what are the functions. So this is kind of not a reformulation of rings, but in a different way. And that's an equivalence of categories. But on this side, you can actually glue. You can glue spectra, such a fine spectra, to get some global objects. You can believe, but we will only be interested in the case where R are the integers, Z. So this is a scheme. You make a geometric object from a space. Let's call it X. Space from a ring. And if you have a more map of rings, ring homomorphism, you can pull back the prime ideals, and so you get the arrow in the other direction. So now this topology, this Zariski topology, as I said, is very weak. And it carries information, but not very much. And if you want a topology which is more like the topology that we are used to, what you have to do is to introduce the so-called étale topology. The étale topology. And of course, I can't do it formally for you, but I can tell you the idea. So in algebraic geometry, the analog of the implicit function theorem, the inverse function theorem doesn't hold. If you have a system of polynomial maps, algebraic maps, which are infinitesimally invertible, then it's globally not invertible, because in polynomials, I mean, you would get algebraic functions, they are not polynomial. So it doesn't hold. And this is the Zariski topology is not good enough for this. And so the solution, there's a very formal solution to this problem. The solution is add more open sets. Except they are not open sets in the usual sense of the word, but a little bit general. So let's see, for example, here we have a map of such affine schemes, for example. And it should be étale. So étale is a certain property which you can formulate in complete generality. And it's in geometric situations, when you're working over a field, then it just says that the Jacobian is invertible. So that the map is locally invertible. So, and now we force a local inverse. By the following trivial construction. So here's our map X to Y, which we want to invert, but there is no map in this direction. Even if you take a very small Zariski open subset, there is no map in this direction. That log is an inverse to F. So we don't find open subsets. So the idea is, instead of subsets, open subset, we say we allow more general objects. We allow étale maps instead of just inclusions to be an open subset. So this guy, where the F was étale, we call open subset. Call it open. Well, not subs. Call it étale open. So the opens are not subsets. They hover over your affine scheme. So now, if we allow as open such a guy, then we have an inverse map, namely the identity. So on this open subset, or this étale open, it's not a subset, this étale open X over Y, we have trivially, we have an inverse. Now this looks like that is a trivial, it looks like completely like a triviality, but actually you can do all kinds of topological constructions. For example, check cohomology and the like, with this more general notion of open set, these open coverings. This is called the Grodendic topology. And the basic idea was due to Serre, who looked at vector bundles and wanted more interesting vector bundles than the risky ones for principle. Yeah. So, and the entire thing you call the étale topology. With this, you could make the étale cohomology, and this was used to prove the Weil conjectures and famous things. So now we have this étale topology, and then we have étale fundamental groups. Yeah? And we write it as pi1 with a little hat. And this guy classifies the finite étale coverings. Yeah. So in this topology, you have a fundamental group, maybe not so surprising. And now let us look at an example. But the étale topology is really the thing we have to use to make these affine schemes somehow look topologically more like the things that we are used to. Let us look at the following example. Let's give ourselves a prime number P. Then we have a projection from Z to Z mod P, which is the finite field with P elements. That's a map of rings. And this gives, by applying spectrum of Fp, which is just one point, the only prime ideal 0 in Fp. But and the topology is trivial, and the structure sheaf is also pretty trivial, essentially Fp. And so it maps to spec of Z. This was surjective, this is injective. So spec of Fp is embedded here. So this guy, the prime ideals are the 0 ideal and the ideals for all the prime numbers P. And then the topology is the cofinal topology. And the structure sheaf is very closely related to Z and its localizations. So now it turns out, now we look at this with étale cohomological eyes. Yeah? For Zariski topology, the dimension is 0. But for the étale topology, the dimension is 1. Because there are coverings of spec Fp, they come from the spectra of the finite field extensions, Fp to the n. For Fp to the n over Fp, the deck transformation group or Galois group is Z mod n. And in the projective limit, which this guy, the fundamental group is, we get Z hat, the profinite completion of Z. Okay, and this guy turns out to be 3-dimensional. Which looks crazy. The general principle is that that the étale topological dimension is 2 times the Zariski dimension. And so spec of Z is an arithmetic curve. It's 1-dimensional. Zariski topology is 1-dimensional. And étale topology, yeah, so the Zariski topology is like the complex dimension. Étale topology is like the real dimension. So this Zariski dimension is 1. Étale topological dimension is 2. Or would be 2 if the residue fields were algebraically closed, but they are not. You get another dimension 1, and so the 3 is really 2 times the Zariski dimension plus 1. Of course, you can prove this, that this is the correct dimension. Now, as I said, the fundamental group the étale fundamental group of spec of FP is the profinite completion of Z. That's almost like Z. And one knows that the étale fundamental group of spectrum of the integers is 0. If you think about this, classifies the finite étale coverings. These are the finite everywhere unramified extensions of Z. And it's an old theorem by Minkowski in number theory, but there are no. So you see, in some sense, this is three-dimensional in the étale topology, and it's simply connected. So if there were a Poincare conjecture, it would be something like S3. But we think of it as S3, except it's not quite compact. There is something in arithmetic that you have to add a place at infinity, and then it becomes compact. We think of the entire thing as S3. But I will ignore this difference. Okay, now. Yes. You don't understand? You don't quite understand? Yeah, it's yeah, for example, you can take a spec FP to the n, spec FP. This is it's a finite étale covering. Huh? Or you could take the thing that we're interested in is number rings, or we can take, for example, spec of Z adjoint 1 divided by P. So this is the same as looking at spec of Z and taking out 1 prime P. And then an étale covering would be the spec of any number ring such that, such that this guy is ramified only at P. And then if you take out P, then it's unramified. And that is an arithmetic example. But of course, you can look at classical algebraic geometry and take some algebraic curve, for example, and to take an ordinary finite unramified extension, in the ordinary sense, that is étale. Yeah, unramified and étale is very close. So geometrically, this is étale except here, yeah? Okay, you're welcome. So now we have the following analogy. So let us call K an embedded circle into S3. So K will be a knot. Embedded circle, which is a knot, into S3. And so here the fundamental group is Z, and the higher homotopy groups are 0. And by the way, here, the higher fundamental groups, that is such a thing of spec of P. They are 0 for I greater or equal to 2. So that's a KZ hat 1 in the étale topology. So it's like a circle. And so this then would correspond to, let's denote by K of P, the spectrum of FP, embedded into, not abstractly, but embedded into the spectrum of Z, or maybe spectrum of this arithmetic compactification that I want to talk about. And these guys are kind of, this is an analogy, yeah? So this is a KZ1, this is a KZ hat 1 in the étale topology. This is three-dimensional. They are both simply connected. And so on, this was mentioned by Manin and independently Mazur in the 60s. this analogy. And people like Reznikov, Kapranov, and several more have thought about this. And the entire field, these analogies, there are analogies which are mentioned in a second between knot theory, that's a knot, and number theory, many analogies. And this field, it's a small field in mathematics called arithmetic topology. And the leader of this field is Masanori Morishita. Who has written a very beautiful book and many beautiful articles on these analogies. So let us mention some. Some analogies, yeah? On the one side, it's known that if you look at the abelianization of the knot complement, then this group is cyclic, infinite cyclic. And in arithmetic, on the arithmetic side, we would look at the abelianized étale fundamental group of spec of Z minus the knot, KP, more precisely minus the spec of FP, which is precisely this, huh? Just another more suggestive notation. And here, that is a certain Galois group, which is known to be the units and the p-adic numbers. It's a cyclotomic extension, and this that's the group. And it's almost cyclic, yeah? It's a finite group cross ZP, so it's almost procyclic like this Z. So it's kind of similar. Now we can look at, okay, so now we look at the maximal extension here, S3 minus K. So we have the knot complement, and we look at the maximal abelian unramified extension. So let's call it infinity. I got this from Mazur. So then the deck transformation group will be Z. Huh? And similarly, here the situation is like this. We have spec of Z minus KP, which is the same as the spectrum of Z joint 1 divided by P, and then we have a map. And so the corresponding maximal outside of P unramified covering is this spectrum of the ring which you get by adjoining all the P to the nth roots of unity. And so here the deck transformation group is CP star. So now we can do something in this situation, and it has been done. It has been done before this analogy was invented. So in knot theory, the most important invariant before the invention of the Jones polynomial was the Alexander polynomial. And how do you get it? You let the generator here act on the abelianized fundamental group of this space, or on its first homology. And then you get, you look at the characteristic polynomial, and that's the Alexander polynomial. So this is the characteristic polynomial of the gamma action on the homology, or the abelianized fundamental group of this covering, this infinite covering. Yeah? That's a standard construction. That's how you get the Alexander polynomial. And in number theory, Kenichi Iwasawa had introduced the Iwasawa polynomial in his study of p-adic zeta functions. And this is, and he defined it as the characteristic polynomial of the gamma action. Yeah? Here it is a little bit more complicated to say what it is, because that's not cyclic, but it's almost cyclic. On, well, the Booleanized fundamental group of this covering, yeah? Spectrum of Z adjoint P, all the P's roots of unity. And so he didn't phrase it like this, but you can also say it's the Galois group of the maximal outside of P unramified, or over the maximal ramified extension of the cyclotomic one. So this sits over this extension. You look at the Galois group, and this small Galois group canonically acts by conjugation on this Galois group. This was the situation that that Iwasawa had studied. And you see these are both instances of the same construction. There are more analogies. So for example, there are linking numbers. If you have two knots here, there are linking numbers. And let's look at them mod 2. Because otherwise we have to orient the knots and it's not clear what we have to do for primes. So linking numbers mod 2 of two knots. K and L. So these guys, I'm very bad at this. These two guys are linked with linking number 1. And if the two knots just sit next to each other, they are not linked. And on this side, the analogous object turns out to be the quadratic reciprocity symbol. And the linking number is symmetric. Yeah? There's definitions where it is not at all clear that it is symmetric. And one proves that's a theorem then. And so this corresponds to the Gaussian reciprocity law. But here we have to say the analogy is only perfect if P and Q are congruent to 1 mod 4. The reason that the other primes are excluded is that S3 is not such a good analogy. It should be a more complicated 3-manifold analogy. And then the other primes are not homologous to 0. So it's not so easy for them. But that is, we have this. That's an analogy. They even and actually, there are proofs, there are definitions and also proofs of quadratic reciprocity, respectively the symmetry of the linking number, which are quite analogous, where you can really translate one set of arguments in knot theory. If you know this dictionary, you can translate it to number theory, you get a proof of quadratic reciprocity and vice versa. Now then there's also nice things like Massey products. So these are higher cohomological operations. If you have 3 unlinked knots, if you have 3 knots, any 2 of which are not linked, you can still make a configuration of 3 knots which you cannot pull apart. So Borromean rings. If I had more time, I could draw it. So then now you must make another one. Probably like this. And then has to go below this one. So with a little luck, now does it work? No, it doesn't. Probably this has to go here. Has to go here. Oh no, that's also bad. No. Okay, let us. You can clearly see I'm not a knot theorist. So let's just leave it as an exercise to make the coverings in such a way that you cannot untilt them. Okay. So there's something in number theory which is called the radii symbol, which was invented in the 1993 to study ramification in certain extensions with quaternion groups of degree 8. And so, for example, this guy would correspond, there's an example here, would be the following numbers, prime numbers 5, 41, and 61. This is a radii symbol, which one can show is non-trivial. And these are all primes congruent to 1 mod 4 in this. And the quadratic reciprocity symbols of the 3 are always 1. So they are unlinked as primes. But the entire configuration is linked. That's an analog there. And also the theory of radii symbols and of the Massey products or more general Milnor invariants can be built up completely in complete analogy. Okay, so these are analogies which were invented before me. And now I will talk about periodic orbits and primes. Periodic orbits, not knots in certain dynamical systems, and primes. So why should prime numbers have something to do with the dynamical systems and primes? And again, three dimensions will appear. Now there is the following formula, very, very simple formula called, well, it's called the product formula in algebraic number theory. And if you take the log, you get this. And we do it only for the field of rational numbers. If you take the sum of all the prime numbers and we take some non-vanishing rational numbers, then for a prime number, we can say with what exponent p appears in F. Yeah? What's the exponent? It's an integer. So for example, if the number is 5 divided by 3, then the order at 3 of this number f is -1, and the order at 5 is 1, and the orders at all the other primes are 0, because they don't divide. So we take these orders, we multiply by the log of p, and then we subtract by the log of the absolute value of f. And this is always 0. This is very, very easy to prove because you only have to prove it for the prime numbers, and then you add all these equations. And if you have a prime number p, then the order, and then this will just be 1 at p times log p. And if f is p, then this is also log p. So it's clear. And for -1, f equal to -1, both sides are 0. So it's always true. So very, very simple. Now, how does it look? It looks like something from geometry. And the question is, what is the geometric meaning of this? Because there seems to be some geometry behind all this. So if you have a Riemann compact Riemann surface and a meromorphic function, then the sum of the orders in all the points of the meromorphic function is 0. Yeah? Because it's known that the degree of a divisor of f is 0 if f is a meromorphic function on a Riemann surface. But this is only a sum of integers, which is 0. This is more complicated. Integer times transcendental number, and then some strange thing here. By the way, the strange thing here corresponds to the infinity in this, which I added to z to compactify. Yeah. Because you can, instead of prime numbers, you can also speak about valuations. And these are the non-Archimedean valuations. They correspond to the primes. And this is the one Archimedean valuation. And to get this type of formula, so that sum is 0, you need to add this. This is kind of a compactification. So now so a single Riemann surface is too simple as an analogy. The real analogy is something more difficult. Geometric analog. And this is called a Riemann surface lamination. Riemann surface lamination, which was studied a lot by people like Etienne Guise, the student Daniel Bertrand, and other people. And so this consists of, so the geometric thing is the following. Some space, which is a closed 3-manifold. At foliation by Riemann surfaces. So f is one codimensional foliation by Riemann surfaces. Foliation means a partition into immersed manifolds, and the partition should be such that locally it is just a product. Locally it's just a product, except that in the product the fibers can, the same fiber which appears locally as different, they can globally, it may be the same lie on the same leaf of the foliation. Yeah. So, and then we need something more, we need a flow, an R action. So this is flow. So an R action, usually action, T and R acts by the diffeomorphism phi T. And the condition is that phi T respects leaves. It sends leaves to leaves. Yeah, the connected components, so the immersed manifolds, they are called the leaves. And for a given time T, the flow may transport the leaves. For example, if you take a trivial foliation M cross R, and the flow just by translating by R, then the leaves are M cross point. And if you translate by a fixed number T, then you are mapped to another leaf. Okay. So this is a structure, and we need, okay, and then we need some technical things such that for the next theorem, such that the periodic orbits are transversal to the leaves. Yeah. Yeah, so some of these orbits will be periodic, and those should always be transversal to the leaves which they hit. And the final technical condition is that the fixed points should lie in finitely many compact leaves. So I will write down a formula now, which shows that in such a situation, we get a very similar expression as above, and then I will explain to you how to get a non-trivial foliation. So you get some idea of this type. So so it's a little bit complicated, the setup. Yeah? 3 manifold foliated by Riemann surfaces. There's also a flow. The flow must map leaves to leaves, should be transversal to the leaves over the periodic orbits. The flow can have some fixed points, but they must lie in compact leaves. Then, of course, the flow will map the compact leaf to itself, because if it maps one point to itself, it has to map the entire leaf to itself. So, and so then we have a theorem, which was noted by Gies, in the case that there are no fixed points, and by my student Kopai, when there are fixed points, and it looks like this. The sum over the periodic orbits I need a condition, which I will mention later. Yeah. Then comes the order in the periodic orbit of a function f. I will say what type of function we're looking at in a moment, times the length of the periodic orbit, minus the sum over the compact leaves. And then something which maybe I don't explain in too much detail, an integral over a tubular neighborhood over the compact leaves, and then some differential form. Anyhow, this entire thing is 0. And who are the players? I have to explain who is f. Yeah? So here, f from our x bar to complex projective space, so C union is a continuous function, such that the restriction to all the leaves are Riemann surfaces. Yeah, restriction to all the leaves, f, is holomorphic. Yeah? So we have continuous functions, and on the leaves, they are holomorphic functions. And also so that the sum makes sense, such that zeros, poles lie only on finitely many periodic orbits. Yeah? We look only at such functions. And then we have this formula. Now, this is the length of the periodic orbit. Okay. This is a little bit more complicated. df is an exterior derivative along the leaf. That's kind of clear. Omega phi is a one form, which is 1 on the vector field generated by the flow, and which is 0 on the tangents to the foliation. So let's not discuss this too much. It is something that comes only from the compact leaves, and it's only a finite sum. Right, what I have to tell you is what the order is. So the order of our meromorphic function in a periodic orbit, this is the following. You take the order in X of F restricted to a leaf where X is a point in the periodic orbit and where it intersects the leaf F. Yeah? And so it doesn't, so we have this periodic orbit, and it was imagine a book, and then we go right through the pages. And the pages are the Riemann surfaces locally, and we restrict the function. And if there's a zero or pole, it has to lie on a periodic orbit by assumption. And then we look at such a point. It goes through some leaf, and then it has a certain order of vanishing, because now that's a holomorphic function point in the Riemann surface has some order. And because it's an integer and it varies continuously, it doesn't matter which leaf we take. Huh? It's always the same. It's always an integer. So now if you compare, you see this looks formally much more similar. We have, in such situations, you can have infinitely many periodic orbits like primes. We have an integer, and you have log p, and this corresponds to the length. And then you have something strange. This corresponds to the compact leaves or the fixed points. So number theory, you have the non-Archimedean valuations and the Archimedean ones. In dynamical systems, they correspond to the periodic orbits, respectively the fixed points, or the compact leaves in which these fixed points lie. So let us note this. You see the primes in this analogy, they correspond to periodic orbits. Gamma, and such that log of p, this number, is the length. And in this analogy, this periodic orbit lies in the 3 space. And now if you forget the parametrization, then your periodic orbit is nothing more than a knot. So gamma, forgetting the parametrization. Gamma is a knot. So it's similar, so we are similar, but this is kind of more refined than in the previous analogy with the knots and the prime numbers. By the way, note that for dynamical systems with good properties of periodic orbits, you have the Riemann zeta function, which is the product of a periodic orbits. 1 minus e to the minus s times the length. And then comes some signs as a recipe for the signs. That's a Riemann zeta function, important in dynamical systems. And now in our situation, in analogy, L gamma, this will be the prime numbers, L gamma will be the log of p. And so this will be this would correspond to the Riemann zeta function, which is something that we want to understand. Now, Riemann zeta functions, often you can understand them better because you are dealing with analytic objects, you have analysis, you have all the tools of PDEs and so on and so on. And that's a much better situation than here, where we can only look at this function and try to do something with it. In this case? Yeah, it depends. If you make good assumptions, which I will do in a second, then they behave very nicely. Yeah, I will be a little bit, I will answer your question. During the discussion, I mean, I will write down a theorem and then it says I will give you one situation where on this situation, the Riemann hypothesis holds. So there's something called the explicit formulas in analytic number theory. Actually, it goes back to Riemann's famous paper, where he looked at some special test functions that's been generalized mostly conceptually by André Weil. And so the explicit formulas in number theory, you can view them as an equality of two distributions on the real line. And the analogy which I'm going to write down is more compelling if we restrict to the positive real numbers. If we do it on R, then there are some differences between number theory and dynamical systems, and I don't have the time to explain where these differences come from and how they can be resolved. But in this case, it looks quite compelling. Now, the formula looks like this. So I said it's an equality of two distributions, in this Schwarz distribution space. So functionals on test functions, so smooth functions with compact supports. And every locally integrable function gives you a distribution. And now we take the function 1, view it as a distribution. So evaluating in a test function is integrating over it, minus rho sum over et rho. T is the variable on R plus, so that's a function of T. As rho are the non-trivial zeros of zeta. Non-trivial zeros, rho of zeta function, Riemann zeta function, plus e to the t. And we view it as a sum of distributions. So, and this is something. So what does it mean? So distribution, as ordinary functions, it converges for no t. But as distributions, it does converge. So we take the sum over e to the t rho. And we have to evaluate on a test function, phi. And this is evaluations of the e to the t rho on phi, which is the integral from minus infinity plus infinity of e to the t rho times phi of t dt. And this guy is usually called big phi of rho in the analytic number theory literature. Okay, that's the way how this distribution is defined. So we have this alternating sum, and this is equal to sum over prime numbers log p times another sum over k greater or equal to 1 delta Dirac distribution at k times log p plus something, an integrable function on the positive real line, which will also give you a distribution. And again, this comes from the prime numbers. This comes from this Archimedean valuation. So we have this formula. It's a very old formula from 1800, except they didn't write it this way. So, and one can wonder what the meaning of this formula is. I mean, it has to mean something geometrically, if we believe in this picture that we are having. And so the foliation analog is this. So again, we have such a system as before with all the properties which we mentioned. And in addition, assume there's a metric GF on the tangent bundle to the foliation such that phi t acts with conformal factor e to the alpha t. Okay, it has to act with some. We assume this. Okay, then the spectrum of the infinitesimal generator theta of the induced action by the flow on the harmonic I-forms along the leaves, which are square integrable. So this is something like df star plus df star df on the I-forms. So like the ordinary Laplacian, except you take derivatives only in the leaf direction. If you have a foliation, then df square is always equal to 0. That you can. It means that the foliation is integrable. So these are leafwise harmonic forms. This will act under this condition on this space, and it will have an infinitesimal generator. And the spectrum of this guy consists only of eigenvalues. So it's very simple. And we call them rho, yeah? So then the condition, if the flow is everywhere transversal to the foliation, so we don't allow these compact leaves with fixed points, huh? And periodic orbits non-degenerate, that is a technical condition. Then again, as this, we have an equality of two distributions on the positive real line. Actually, a similar theorem on R, yeah? But I don't state it because it looks a bit different than the other one. So 1 minus sum over rho, e to the t rho. These are now the eigenvalues, yeah? Plus e to the alpha t. Alpha was this conformal factor, is sum over, you can write it now for me. Primes are periodic orbits. Yeah. Then comes, of course, the length of the periodic orbit. Then comes the sum k greater than 1 of Dirac distribution in k times length of gamma plus nothing. Well, I omitted because we did not allow fixed points. So this formula is a special case of general transversal index theorem for R actions, proved by Álvarez-López and Kordyukov. And I asked them to prove a theorem which allows fixed points, which is much more harder because then it's not a transversal index theorem, but something more complicated. It's like passing from a compact situation to a non-compact one. So it gets really complicated. And then together with Leichnam, Eric Leichnam, using much more, so it's much more difficult. They get such a result where here we have something and we allow fixed points. That's very recent and unpublished. So, and this is a transversal index, yeah, of an elliptic, of a complex which is, well, of this elliptic complex where the differentials are along the leaves. So because it's transversally elliptic to the R action because we said the flow was transversal to the leaves. In such a situation, you can define an index, but it's not an integer as usual. but it is a distribution. If you want, I can explain to you easily how it is done, but maybe I don't have the time because I want to mention some progress. So this, what I forgot to say is that, moreover, in this situation, the real parts of all the eigenvalues are equal to alpha half. So for alpha equal to 1, which we would have here, the real parts would all be 1/2, which is the Riemann hypothesis. However, you can prove that if in your analogy between number theory and these foliated systems, you only allow manifolds as your topological spaces, then automatically only alpha equal to 0 is possible. So if you want a different alpha, you have to allow more complicated spaces than manifolds. And the simplest thing is something like a ball. You have to allow spaces which locally look like a ball cross something totally disconnected. So it's very well known in the theory of dynamical systems called generalized solenoids. And this is the minimal complication which you have to allow. And very long ago, I made an example where actually 1/2 appears in the dynamical system on such a more general space. But this was, I think, 15 years or 20 years ago. And so, of course, when you see all these analogies between knots and the one between dynamical systems, you think there must be something, yeah? And the question is, what is it? So I've thought about this problem for more than 20 years. And 2 years ago, I finally saw something, yeah? How to make a construction, an actual construction. And very happily, at the same time, Peter Scholze and Robert Kucharczyk, they wrote a paper on topological realizations of Galois groups, realizations of Galois groups of fields as topological fundamental groups. And so the ideas between these ideas fit together very, very nicely. And so now I can tell you something new. I can give you the construction of a foliated dynamical system, which actually knows something about the prime numbers, or which knows everything about the prime numbers. But unfortunately, it's not yet the right one. In the p-adic analog, I know how to correct it to get the right one. In the most interesting case, I don't quite know how to do it, but I have an idea. So now new, yeah? After 20 years. And this is in the preprint dynamical systems for arithmetic schemes on the archive. So what is it? The construction is as follows. I will not explain such a lot about the objects that I use because that takes too much time and I don't have a lot of time, but you get maybe a feeling. So we start with a scheme. As I said, a scheme consists of a topological space and a ring of functions on it. For example, X could be spec of Z. Or even something really small, like the spectrum of the p-adic integers, which is just 2 points. So that's a scheme. And we want to make a new space from the scheme, namely called the rational bit space. So it's a space with a structure sheaf. The underlying topological space is the same as the one of the scheme, but the structure sheaf is way more complicated. Namely, we take the sheafification of the rational bit vector sheaf. Yeah, bit vectors are very well known. There, usually the p-typical ones are used, and there's something called the big bit ring. And inside the big bit ring, which consists of formal power series, one can look at the formal power series which are actually given by rational functions. That's called the rational bit ring. It's not a sheaf, but you can sheafify and then you get a sheaf of rings. But it's much bigger than this original sheaf. I can explain more. And now we define points of such a sheaf. So for another scheme S, yeah, we define what is a point, morphism between these ringed spaces. So if you have two ringed spaces, you know what a morphism is. There's a morphism of ringed spaces. But for schemes, you know, there has to be a locality condition. Otherwise, you get too many morphisms. And here, the crucial thing is to find this locality condition. And the condition is that this morphism of ringed sheaves for every point of S gives you a map, a ring homomorphism. Now you have a natural projection to the residue field here. And here too. And the condition is that such a thing must exist. Only such morphisms are considered, okay? So that's, you have to make some construction, of course, if you want to get new spaces. So now this construction, which is very general, just a few lines and then I'm done. Okay, now we set. So we take the rational bit space. This is the set of these such morphisms F from S to this space, which I just defined. And now, and by the way, this space has commuting Frobenius operators. F nu for all F in N, which is just the positive integers. Yeah, but it's a nicer object. And I view this as a multiplicative monoid. And so because the bit vectors and rational bit vectors, they have commuting Frobenius operators, and on the points you also have commuting Frobenius operators. So now let's change the notation a little bit. Instead of x for our scheme, we write x0, script x0, let this be an integral normal finite type over spec of z. So we can take everything we can do with spec of z. And then let's abbreviate the points of the rational width space of this scheme x0, spec of z, for example. And now we take spec of c-valued points, or we just write simply c-valued points. Yeah? So that is the beginning of our space. Now this has an operation by the monoid n, by these Frobenii, but the n's, the Frobenii are not invertible. So now brutally we invert them. So we form that's a construction, standard construction. We form the co-limit over them. It's the same construction that turns the natural numbers into the rational numbers. That's a formal construction. And now this guy has an action by the quotient group of the monoid, namely the positive rational numbers. And now we're almost done. Our dynamical system, what we do is we take this space, these complex points, we take the product with the positive real numbers, and now we have an action by the positive rational numbers by the Frobenii here. And we also, it's a subgroup here. And now we divide it out diagonally. I think you write We write this up here. Or maybe mod Q star diagonal, yeah? Okay, so this is the guy. So it has a flow. Phi t of, so an element here will be a pair, the equivalence class of pair, P and U. And it is mapped to e to the t times U. That's our flow. And the one-dimensional foliation, it's not a real foliation, but it's just the images of, well, we take these guys, cross points. Yeah? So that gives you a partition locally. Well, gives you a partition. This is kind of foliation. And then the first theorem about this thing is that the closed points of x0, so in the case of spec of z, this will be the prime numbers, p in spec of z, for example, yeah, they correspond bijectively to not individual periodic orbits, but to compact packets of periodic orbits of length log of, well, closed points x0. They have a residue field which is finite. You take, this is the number of elements, you take the log. So of prime number p, this is just log p. Yeah, and there are no, and in each packet, it's fibered over a compact space, very easy compact space, and the fibers are just the periodic orbits corresponding to the closed points, and they all have the same length. So it's not one periodic orbit, but it's a whole compact family. It's like invariant tori in Hamiltonian dynamics, except the transversal structure is totally disconnected because it's fibered. It's fibered over the following compact group: automorphisms as a group divided by automorphisms as a field. So this is something like z hat star mod p to the z hat. That's a compact group. It's fibered over this. Okay, and these are the only orbits, and these spaces are very highly non-connected. And it's a pretty difficult theorem to prove that x0 is actually connected, because otherwise, if it's not connected, then it's very easy to make such spaces. It's surprisingly difficult. You need a kind of resolution of singularities in characteristic P. Yeah, it's difficult. Okay, so I can go on. This is the beginning of this paper, but I have no more time, and I think I spoke 5 minutes late, I think. Thank you very much. Yeah.
Thank you for this fascinating lecture. There are questions?
Yeah.
Can we say something about the dimension of this?
Yeah, these spaces are too big. They're infinite dimensional.
Oh, okay.
Yeah, definitely not three.
Like three-dimensional. Like if you start from Z itself.
So spec Z itself is still infinite dimensional.
Okay, it's not three-dimensional.
Not three-dimensional, no way. So one thing I did, I looked at all the periodic orbits and took the topological closure, yeah? Because then that's the smallest system which contains all the periodic orbits. But even this system is infinite dimensional. And so, of course, I've been looking for a good subsystem, yeah, or modifications, but I did not yet find it. However, we can do the same construct, or we can, instead of working with the arbitrary x0, we work with this very small little scheme spec of ZP. And then let's look, for example, at this space. Then we look at x0 hat. So this is our x0. And now we take the CP value point. C is the algebra, the completion of the algebraic closure of QP p-adic numbers. So that's a p-adic guy. And this is also infinite dimensional, too big. However, in here, there's a very, very natural subsystem. Very natural. It immediately sprang into my eyes. And I studied it, and I thought, what would in the best world, what could this good subsystem be? Yeah? And I thought, maybe it is the curve of Fontaine-Falk, which they introduced to revolutionize p-adic Hodge theory. And that would be, yeah, and it is true. There's a bijection between the points of the subdynamical system, which I found, and the points of the Fontaine-Falk curve. So it's not so easy to prove this, but I just hoped, yeah, in the best of worlds, and it turned out to be true. So that was really nice. The condition here is kind of when you look at these guys, you look at essentially multiplicative maps, and then mod some Galois action, which brings in some additive conditions, but it's still too general. And the condition in the p-adic case is that the guys should not only be multiplicative, but modulo p, they should be additive also. That's a super nice definition. And so, of course, I ask myself, is the same, can we do some similar things for the c-valued points? But then mod p is, to take mod p is nothing which you can do in the C world. It's not clear. These spaces are related also to the work to the simplest case. No, the constructions by Scholz and Kucharczyk, they are related to the case where the base scheme X is the spectrum of the field, so it's zero dimensional. And they already looked at the cohomology and also found the cohomology is too big. Yeah? So, for example, they would find a cohomology like an exterior algebra, and if you're starting with a field F, something like exterior algebra over F star or tensor Q, which is too big. And the thing, of course, what you want is you want the Milnor K theory. So, yeah. And so the spaces are not yet right. We get, this is too big. What you want would in this case be something like this. They already point this out in their paper. And the same problem persists here. So the zeroth cohomology is okay, but the higher ones are not yet okay. Yeah.
So I have two questions. One is, do you have concrete consequences for p-adic Hodge theory from your interpretation of the curve appearing in the space?
I did not think about this. I just made a bijection. I didn't even give my spaces a topology in the p-adic case, and of course not an analytic structure. Well, the construction p-adic Hodge theory, they work only if you use the specific situation over the p-adics, whereas my construction works globally, but it's a non-trivial fact to show that in the p-adics it's in bijection with the untilts. So of course the hope is that you have, if you make the correct modifications, we get some global object which specifies then in the p-adic case to the well-known constructions. But there are so many p-adic techniques, and it's such a highly developed field. I don't want to contribute there. I want to prove the Benson conjectures, or at least understand them. By the way, what I discovered very early on was that proving the Benson conjectures, what you need to do is to have a theory of weights. It's basic for étale cohomology of varieties over finite fields. The theory of weights means the generalized Riemann hypothesis for all arithmetic schemes. So that's kind of a first requirement if you go to deeper things like Benson conjecture. So this was a little bit frustrating.
And so the second question was, so in this work or paper of Kucharczyk and Scholz that you mentioned, I mean, there is this crucial condition that your field has all the roots of unity contained in it. So otherwise you can't do anything. So does this appear in your?
Well, they do it to get something connected, I think. If you accept that these spaces don't have to be connected, the spaces at this stage don't have to be connected, then you don't need that condition.
Other questions?
To understand the definition of W, like before the simplification, you take for every open the bit vector
The
of
rational bit vectors of the sections, yes.
rational.
That's a separated pre-sheaf, but they don't glue, so you sheafify.
This with the two measures with zeta function. What was delta k log p? There was a delta k log p, if you remember your notation.
Delta k.
Just the primes, and just summing over.
Okay.
Oh, sorry, yeah, Dirac delta. Yeah, sitting in the logs k times log of p,
Okay.
respectively k times the length of the periodic orbit.
Okay. So the dependence on p was only on the last version. Okay, thank you.
Summing over the prime powers.
Yeah, for example.
Are there results of distribution of these orbits in this analogy, especially in this new analogy
Yes, of course.
with the primes? So because the analogy goes closer, as you explained,
Yes.
closer and closer to the primes with respect to the naive analogy provided by the function fields.
This is true, but I did not study this.
Okay,
It's
but
because
do you think that some distributional result can hold?
I'm sure one can prove distribution results in this context, but you're not so interested in the periodic orbits, and
Yeah.
you're interested in the prime numbers, and working with manifolds will not. You know that it's too simple. Huh? You can never prove working only with manifolds and their dynamical systems foliations. You can never prove anything about the prime numbers. You need much more general spaces.
Yeah. That might be related to yours. It's just, of course, it's fascinating to try to get this approach to get more information. But I wonder if there is any interesting application on the other side, because the theory of the Riemann zeta function is developed in many ways. And for example, using these explicit formulas, one can prove very nice theorems about prime gaps and the usual prime number theorem. How does this translate in an interesting way to any situation where you want to count the number of periodic orbits of a certain length or estimate the different lengths? Might be something.
So, as I said, these are very special dynamical systems where you have this transversality condition. But of course, for geodesic flows also, the corresponding questions have been studied a lot. But generally speaking, I think that on the geometric side, you have many more tools than on the analytic number theory side. So, of course, you could take analytic number theory tools and translate. But I think you have better methods in the geometry. Yeah. Yes, sure. Yeah. Yes. Yeah, but as I said, I did not study my particular dynamical systems. I think these conditions are very restrictive, and I don't know how interesting they really are. They were only for me, they were motivational.